Hi everyone, and welcome to this episode of PhET Labs. In this video we're going to be talking about strong and weak acids and bases. Okay, so some of the things that we're going to be looking at, we're going to recap some of the definitions of what we mean by an acid and a base, especially when we're thinking about the Lowry-Bronsted definitions, which is the main ones that we're going to relate to in this particular area. So we're going to spend a bit of time recapping those definitions, and then we're going to define this what we mean by strong and weak. Okay, as in not the same as concentrated versus dilute. Okay, that's the first kind of preview of one of the main points we're going to make. And then what we're going to do is we're going to look at a PhET interactive. Okay, so we're going to flick across to an interactive that you can have a look at on the PhET website, which helps to visualize what we mean by a strong and weak acid. Okay, let's begin. So remember that when we're thinking about the Lowry-Bronsted definition of acids and bases, so we're thinking about an acid being a proton donor. Okay, so a proton representing an H+ or hydrogen ion, and a base being a proton acceptor. Acceptor or receiver. You might prefer that kind of language. Okay, so that is an acid-base reaction. So when we are combined, acid and base are reacting together, is also known as a proton transfer reaction. Okay, because we can recognize that now when acids and bases are reacting together, that it's actually involving the transfer of a proton from one of the species to the other. Okay, as in when we have NH3 reacting with hydrogen chloride gas, we end up with NH4 plus Cl-, where a proton has been transferred from here to this nitrogen to give us our products. Okay, and so what we're now going to have a look at is this idea of we're going to compare two acids. Okay, so the first acid we're going to look at is hydrochloric acid interacting with water, and then this second acid that we're going to look at is this is called acetic or ethanoic acid interacting with water. Okay, so what we're seeing is that so we're going to draw these as Lowry-Bronsted acid-base reactions. Okay, we're seeing water molecules. Well, I'm deliberately drawing here water molecules on the left-hand side. Okay, so what we're seeing, so when hydrochloric acid or this HCl compound interacts with water, what happens is that we get, so this one acts as an acid, and this water acts as a base. And what happens is that this proton is transferred from here to here, giving us a chloride ion and hydronium. Okay, so that's the general sort of reaction that we have here. And so what happens here is that, I might just clear that off for a second, is that we recognize that all the particles, all of the molecules of HCl over here split or will react or lose their protons, transfer their protons to form chloride. Okay, I'm going to show you another way that we might visualize this. Okay, so what I'm going to do is I'm going to use some of these colored little buttons to help represent molecules of our HCl. Okay, so I'm going to set up 5 of them, if space will let me. Okay, so 5 of them underneath each other, just like that. Okay, so I might nudge them up a bit. Okay, so what we're saying is that so let's say that the blue represents our protons, and then the red represents the Cl part, the H and then the Cl. What we're saying is that, and then maybe what I might do is I'll use some yellow ones to represent water molecules, just so to try and help the visualization. Okay, realize all of a sudden we've got all these colors going on. Just bear with me. Okay, so what we're saying is that every molecule of HCl will donate its proton toward a water molecule. Okay, So the proton is donated to a water molecule to make H3O+, and we're left with Cl- over here. Okay, so we're seeing that each one of these will undergo this process. Okay, so we're getting this different pairing happening that's over here, and we're getting all 5 of them. Okay, so we would call an acid like this a strong acid. That is, it fully dissociates so all ions, so all particles broken up. Yeah, so we would say that this particular example is a strong acid. That is, all the particles of HCl have broken up. Okay, so now let's clear these away and look at a slightly different example. Okay, so let's have a look at acetic acid or ethanoic acid reacting with water to form the acetate ion and hydronium, like this. Okay, so we're going to represent it in the same sort of way. Okay, so we had so again we'll do 5 particles of acid and corresponding water particles. Okay, now so when acetic acid or ethanoic acid does this process, what we notice is something different, is that not all of these acid particles end up reacting to form over here. So what we might see is perhaps this one donates its proton to form hydronium with the acetate left behind. But then these other ones here remain unreacted. Okay, so what we're seeing, and then what we also can see is that these two can react together to reform our acid and our water. Okay, so in this situation that we've got 2 things going on. The first one is that this is actually an equilibrium, okay, because we can go backwards and forwards. And what we can see is that it's not fully, so it's only partially dissociated. Okay, because you can see we've got some here, but most of them remain over here. So we call this an example of a weak acid. Okay, so it only partially dissociates / ionizes. Now what we see is that there's with weak acids is that we see degrees of, you know, or the kind of, maybe you might want to call it a spectrum of weakness for an acid, or a base as well. We see the same behavior in bases as well. So that a strong acid will always fully dissociate, whereas a weak acid may dissociate to different degrees. It might be 1%, it might be 10%, it might be, you know, like 0.01% dissociation. Okay, so that it varies. Okay. Now, one thing that I do really want you to stress here is that strong and weak relates to how much it dissociates. It does not relate to how much there is in solution, how concentrated it is. Okay, because one of the problems here is that we tend to use words like strong and weak as though we were, say, describing something like cordial. Oh, it's very strong, that it's very, you know, which is what we're essentially saying is it's very concentrated. You know, that there's a strong amount of flavour in that glass of cordial, versus a weak cordial, you know, maybe even there's a small amount of flavouring, so it's rather dilute. Okay, but in chemistry that we're using the term strong and weak very deliberately. Okay, we can also very quickly, I'll show you examples of strong and weak acids, weak bases, just to show you that it's not just limited to acids. Okay, so we'll have a look at an example of a strong base. Okay, so we've got sodium hydroxide dissociating into sodium ions and hydroxide ions. Okay, so if we say had, let's say we've got red and yellow representing our sodium hydroxide, okay, and all of them are splitting apart into their separate ions. Okay, so it's fully dissociating, fully ionizing. Okay, whereas then if we say, look at an example of a weak base. Okay, so a classic example would be ammonia reacting with water to form ammonium and hydroxide. Okay, and this is, like all weak things, this is an equilibrium. Okay, so let's say, so when we're looking at ammonia being an example of a weak base, I'm going to visualize it very slightly differently. I'm going to show the water molecules as being these two combinations here, and so the blue still representing our proton. But what we're saying is that in this situation that that proton is being transferred to make the ammonium, and leaving behind, we're going to represent this yellow as the hydroxide. Okay, but now rather than this happening for all three of these, that perhaps only one of them out of these three will actually undergo this. The others will remain as they are over here on the reactant side. Okay, so it doesn't fully dissociate or fully ionize in this process, but only partially. Hence, it's a weak base. Okay, I'm just going to very quickly show you the PhET interactive that you're going to use for the next exercise. Okay, so here's a quick introduction to this interactive on acid-base solutions. Okay, so what we're seeing here is that it's helping for us to illustrate what different solutions are like. So you've got water, strong and weak acid, strong and weak base. Okay, and so helping to visualize what the particles are doing. So you can see, as well as being able to measure the pH. Okay, I'm going to take that out for now because I just want you to visualize the particles at this stage. Okay, so for a strong acid, so we're seeing that all of our HA over here has been used up to form A- and H3O+. Okay, so we still have lots of solvent, lots of water molecules around, don't forget that, but we don't have any of our original acid left. Whereas when we look at, say, a weak acid, we have lots of original acid and some dissociated of the conjugate base. If I show you that in terms of a graph, that we're seeing that we still have some of the original starting material, we have equal amounts of our two products, which is less than what the original stuff we start with. Okay, for a strong base, we're seeing the same idea that the original structure of that base has separated into its two ions, whereas with a weak base, such as ammonia, that only some of it has ionized to form the conjugate acid. Okay, so hey, feel free to have a bit of a play around this interactive and see what else you can find out. Alright, thanks very much for watching. Bye for now.